Welcome back, everybody. The next and final talk in this session will be Logging for Scientific Computing, Debugging, Performance, and Dask by Itamar Turner-Trauring. Over to you.
Hi, my name is Itamar, and said I'll be talking about logging for scientific computing, although I should add that in practice, much of what I'll be talking about applies to data science or quantitative finance, anywhere where you're doing large scale data processing. So there's a little bit of background and how I got to this point. I'm a software engineer. I've worked as a software engineer for most of my career. But until a few years ago, I've never done any scientific computing. But then I got a job at a local startup that was building a gene sequencing device, doing spatial gene sequencing. And so I got to learn a lot about scientific computing and how it differed from the kind of distributed systems and other kinds of software that I'd written before. And there's a bunch of things I learned, and I would like to, in this talk, to focus on 3 of them. We'll see how logging relates to all 3 of them. So the first thing that I discovered is that, not surprisingly, scientific computing involved a lot of fairly complex computation. The bulk of what I ended up writing was processing these 3D volumes of images that came out of the microscope and sort of extracting information out of them. This was a series of steps, and they were fairly complicated and involved a lot of math from applied mathematicians and biologists who actually understood the system. And so this was fairly different from the kind of software that I'd written, say, doing flight search or a web application. They don't tend to have that level of complexity. The other difference is that scientific computing, as I encountered, was typically these long-running batch processes. So you load in some data, you do you run all these computations. It takes a while. It might take an hour, it might take 10 minutes, it might take days or weeks in a really massive process. And you write out the data at the end. And the final thing I learned, the reason we're all here, is that when you are doing scientific computing, Dask is a really useful tool. So I ended up using it to scale from one processor to many processor. And there are people here who are running in thousands of machines. So Dask is a really useful tool. And so that will shape what I talk about going forward. And so for each of these things that I learned, there was a corresponding problem. And so the first problem is, if you have these complex calculations, figuring out bugs can be tricky. You don't necessarily have an exception in your logs. You might just have a result that's clearly garbage. Just as an example, if you're doing gene sequencing, maybe the results say that 90% of the genes were this one gene, and then you talk to the biologist, and the biologists say that gene only appears 1% of the time. And so the result is wrong, but it's not clear why. And then the second problem is, because if you're running these batch processes that take a very long time, this can get this is problematic in that, like, the time it takes you to run things can be too long. It might be very expensive that you're using all these compute resources because you're scaling up, and now you're spending all this money in cloud computing. Maybe it's just the feedback loop is too slow. And so having long-running batch processes, you typically will often want to make them faster. And the third problem, since we've decided to use Dask, is when we solve the previous 2 problems, how do we solve them in a way that works well with Dask? And so these 3 problems are going to be the structure of the rest of my talk. So the first problem is, why is your calculation wrong? And the issue here again is the combination of the complexity of the calculation, all that math, all those numbers, where a very slight error can result in a very wrong result, and the fact that you have a slow feedback loop. So imagine you're running your batch process. It's finally done. It only took 12 hours. Could be worse. And the result is wrong. This is a unpleasant situation to be in because you can't just try, you don't really want to try something different and run it again and see what happens. And so how do you solve this? You can try running with some test data. Right? You can have like simulated inputs to your process. And then you, like in my case, I would simulate the scan from the 3D microscope and run it through and then see if I get the same results or not. But generating realistic data is hard. After I left this job, some people with more expertise than me actually spent some effort on that, but it's not easy. And in practice, often you'll only have problems with the real inputs. Like no matter how good your simulation is, everything seems to work. You feed in your real data and then the output's garbage because real data has noise you can't simulate correctly or something. You don't really know. For a lot of software, the way you would approach debugging is the debugger. Like you can sort of step through your code, look at the intermediate values, see what's going on. But if your process takes 12 hours to run, this is not a feasible solution. Like you're not going to figure out what's wrong with the debugger. Like it's not going to happen. And so what you would like is when you get a bad result, to have a retrospective record of everything that batch process actually did, all the work it did to get to this result. Which is to say, what you want is logging. You want a record of which functions called which other functions. You want a record of the functions input as outputs. You want intermediate values. And in an ideal world, you would actually want a record of every single thing your program did from beginning to end. So you could just play it back and zoom in on and watch it and figure out what went wrong. In practice, when you add logging to your application, like there are costs to logging. You probably don't want to log the 2 GB array or data frame that you're continuously changing, although there are ways to solve this if this is a thing you really need to do. So in practice, you're probably not going to log everything. But if you write log messages saying what you've done and what called what and inputs and outputs, you can go back and debug your application at least some of the time, or at least get a hint of where things started going wrong. So when I started doing this, it just so happened that I had created a logging library, which was originally motivated to debug very complex distributed systems. And it turns out that this is actually quite useful for scientific computing because of the way it works, which is very different than most logging libraries. For example, the Python standard library has a logging library, but the way the Python standard library logging works is it's just a series of isolated statements. This thing happened, this thing happened, this thing happened. And connecting them all is actually quite difficult. And as we'll see, Eliot lets you create a narrative, a trace of what happened with causality. And as part of my work at this job I used to work at, I added support for logging NumPy objects. I had integrations with Dask. And you can read the documentation on this website, which I'll also link to at the end of the slides. So let's look at some actual code. So this is an example of some code that is buggy. And it's a trivial piece of code. In the real world, you would just go and read the implementation and find the bug. But I'm just doing this in order to make everything fit on a slide. I'm just doing this as a small thing for illustrative purposes. So we have a function that lets you add two numbers. Function lets you multiply two numbers, and then we have this function that multiplies and sums. So what it does is it takes three inputs, A, B, C, and it adds A and B, and then multiplies it by C. And then our overall program runs this function with inputs 1, 2, and 4. So what we expect to happen is for it to add 1, 2, which gives us 3, multiplied by 4. So 3 times 4 is 12. So when you run this program, we expect it to print the number 12. When we run it, we get the number 0. So there's a bug in this code. And again, this code is utterly trivial, so you could just go and read it. But real code that you're trying to debug, it can be quite difficult given hundreds or thousands of lines of calculations to pinpoint where in there you introduced some buggy code. So let's add some logging. And so I'm going to use the Eliot API called log call. And Eliot has a bunch of APIs for generating log messages. This is the simplest one. It makes things easier to fit on the slide. But there are other more sophisticated and powerful APIs. What log call does is it's a decorator for a function, and it will log the inputs to the function, and it'll log the output of what the function returns. And if the function throws an exception, it'll log that exception. And so you can do this with a standard logging system too. The fact that it's logging inputs and outputs is nice, but it's not sufficient on its own. And we'll see in a second what Eliot adds beyond that. And in addition to just adding those, couple lines of annotations, and I guess 3, because we want to add to multiply sum. In addition to adding the actual logging, we need to write our log file somewhere. So here we import to-file from Eliot, and then we say, you're going to log to this output file, out.log. That's where our log messages will go. So we run our program, and again, we get 0. But this time we have a log file. So we can run a program called Eliot tree on the log file, and it prints out a tree of log messages. And this is where Eliot diverges quite a bit from, for example, Python's built-in logging library. In Eliot, the sort of fundamental unit of logging is an action. An action has a start, and it can have some fields or inputs that go along with it. It has an end, so with a result, where you can add a result field if you have one. And actions can have child actions. So in this case, the multiply sum action had add as a child and then multiply as a child. And so because we have a tree of actions and we can see the results of the actions, we have basically a trace of the calculations the program did with causality. We can see what caused what. So if you read through this, we can see we had the multiply sum action with inputs 1, 2, and 4. And that started the add action with inputs 1 and 2, and the result was 3. And then we multiply action with inputs 3 and 4. And if we look at the code, we can verify that that 3 came from the result of the add. So we multiply 3 and 4, and we get 0. And then the overall result is 0. So if we're looking at these logs, we can actually see that the place where things went wrong for our overall calculation was this particular function multiply. And so now we by seeing it and we can see this not just multiply in isolation, we can also see the whole context. So we can see how the problems percolate throughout the code, how the error in multiply that returning 0 then became an error in multiply sum that returned 0. And I should know that Eliot tree's output is kind of different. It's rather more verbose. It includes things like timestamps. And so for all these slides, I've edited the output by hand just so it fits better on the slide. But I didn't add anything that wasn't there. I just made it more succinct. So that was our first problem, debugging problems in your code. And the next problem we can look at is figuring out why your code is slow. And this, in some sense, slowness comes with the territory, like you're processing a lot of data, you're doing a lot of complex calculations. But the fact that things tend to be slow doesn't mean you want them to be. Like if you can get something down from 6 hours to 3 hours, you've cut your computation costs in half, you sped up your feedback loop, you get results faster. And so if things are too slow, you're going to want to spend some time speeding them up. And the traditional way of doing this is with a profiler. So for example, you can use a sampling profiler, which has very little runtime overhead. So you can just run it on all your production jobs. And it will sample your code and see which functions are called the most, are running the most. And the functions that are running the most are the ones that are slowest. And so you run a profiler and it tells you function F is using up a lot of time. Now the problem with this, so this is useful. This is a good starting point. You figured out which function is slow. But this function might be fairly complex, and you might look at it and say, I feed all these inputs in, and they're all fast, so what's going on? And the issue is it is quite possible for a function to be slow in some inputs, but fast on others. And a profiler can't tell you that. A profiler would just tell you this function was slow some of the time. And so even if you've pinpointed the function, you won't necessarily know which inputs are making it slow. The system that inspired Eliot. The demo the author used was a distributed Scrabble solver he wrote. And he was able to, the demo was basically figuring out that one function in the Scrabble solver was extremely slow, but only if it had as input 2 blank tiles as the letters it took in. And so if you just fed in regular letters into the Scrabble solver, it was quite fast, but only if you fed in blank tiles, the solver was it slow. And a profiler by itself just can't give you that information. So this is, however, is where Eliot becomes useful, because everything in Eliot and logging is structured as an action with a start, a finish, and an elapsed, and a start time and a finish time. Eliot also can calculate the elapsed time of each of the actions in the tree of actions. And Eliot, as we saw, is also logging all the inputs and outputs of your computations, assuming you've added the sufficient logging. What that means is you can combine those two. You can combine the elapsed time to find the slow functions or the slow parts of your computation, and then you can use the inputs to figure out which inputs are causing something to be slow. So let's look at an example. So here I'm going to use a different Eliot API for logging. Instead of using a decorator, it's a context manager. So we say with start action, I'm going to say we're going to start an action called main, and here's one of the inputs so that gets logged. So this doesn't have any impact on the actual running program. This is just logging code. And then we do the actual computation, which basically says for each x in the x's, call the complex calc function, and then store the results, and then do another computation on them. This is completely made up code. And let's say our profiler tells us that complex calc is a slow function. That's nice, but it doesn't tell us what inputs are causing it to be slow. But we're using Eliot. And so we can run our program. And if you use Eliot tree on the resulting log file, and then we just search for our function, or rather for the action. I guess there's a bug there, but so we search for the action, and we see that complex calc was called with 13, minus 12, and 4. So the action was called 3 times. And for each of the actions, we have actually, it tells us the elapsed time. And so we can see this elapsed time is 0.1 seconds. This one is 0.2 seconds. This one was 10 seconds. So the minus 12 input was the one that caused complex calc to run slowly. And so unlike a profiler, which would just tell us that complex calc is slow, from the logs, we can figure out that complex calc is slow with this particular input. And again, this is much easier with Eliot because everything is structured as an action with a start and a finish. And so timing information, how long things elapse, just falls out naturally from the log messages. It's not a thing you have to plan for very much. It's just inherent in what Eliot's tracking for you. So far we've talked about using logging to find bugs in your code, using logging to fix performance problems. And the final problem is we want to use logging inside Dask, which is why we're all here today. So how do you match log message to Dask tasks? So as you may know, Dask doesn't, when you ask Dask to do a computation, it's actually 2 steps. The first thing you do is you build up a graph of tasks. You say, I want you to do this and then this, then I want you to combine these results and then do this other thing. And none of the code actually runs at that point. You're just creating a graph of things that will run. And then eventually you say, you take that graph and you hand it to Dask and you say, please compute the results of this. And so all these tasks are basically feeding information to each other. And so there's causality. The first task calculates a result, and then the result is passed into the next task, and maybe another task feeds into it. And so there's a data flowing through the graph in one direction, which is how information is being shared, to simplify. It doesn't have to. And we'd like the logs to reflect that causality. We'd like the logs to show us that this task, log messages in this task were part of a context of a task that was started from another task. And so Eliot's structure of a tree of actions is a fairly good way to represent that. It's not perfect. One's a task, one's a tree, and one's a graph, but it's quite nice. And so Eliot has some built-in Dask support that lets you do this pretty much automatically. And so this is how you use it. So we have a couple of functions, multiply and add. Again, we're just going to decorate them with log calls so the inputs and outputs are recorded. And now we're going to have this function here that builds the computation graph. So it doesn't actually do any work. It just builds up the graph that we're later going to run. So we create a bag, which is a pile of objects. In this case, the number is 1, 2, 3. We say for each value in the bag, I want you to run the function multiply, which multiplies by 7 by default. So we're going to multiply all these numbers by 7. And then we call the fold operator that sort of combines all the results back into one result. And we combine them by adding. So we're going to combine we're going to sum everything up. And so far we just have this logic where we've added a little bit of logging. And next we need to write out our log files. And so we're going to use distributed on a single machine. So we're going to have worker processes in addition to the main process. And we don't want we don't want to share the same log file across multiple processes because the messages will all stomp on each other. So what we do is we have a function that initializes Eliot logging where the file name uses the process ID of the process. Each process will have a unique process ID. And so process 123 will write to 123.log. And so first we initialize logging on the main process. It's driving all the work. And we create a client for Dask distributed, and we ask to start 3 worker processes. And then on the client, we run start logging. And so that gets sent to all the workers, and all the workers initialize their logging. And so now all 4 of our processes are set up to write logs to disk, each one in its own log file. There's like a little boilerplate code you put at the beginning of your application, just to initialize your log files. And next, we are actually going to run our computation. And typically, to run a computation, you'd create a bag, and then you'd call Dask. You can call Dask compute with a bag, and you'll get back a result. In this case, instead of using dask.compute, we're going to call eliot.dask.compute with trace, which is a wrapper around Dask compute that instruments the graph so that all of the tasks inside the graph are contained inside Eliot actions. And so basically you get this logging context for the graph that is where it will, all your messages will know which tasks they came from and which tasks we're feeding into them. And we can do this because we have the whole graph, so we know how everything's going to flow. So if we run that and look at the results, so here I'm just grepping out the first, the outline of all actions. So we can see we have a top level task and it we're doing a Dask computation, and that started a Eliot remote task, which means this passed either a thread or process boundary. And so it did a multiply and then a multiply and a multiplier, all as their own remote tasks. And then the 2 adds were in a single remote task. So it looks like the adds actually ran on a single process together in the same place. So even like just looking at the high level structure of the tree, we get some hints of how Dask distributed scheduled our tasks. And again, I'm filtering here just to show the first line. This is not all the data. It'd be hard to read on a single slide. If we zoom in, we can actually look at particular tasks here. And so, for example, we can see the multiply action had inputs 1 and 7. And so the result was 7. We can see later on there was an add that took a 7 and a 14, and the result is 21. And so we can see all of our computations in the context of which Dask tasks they ran in. And we have some sense of causality. And so this instrumentation is fairly transparent, but it has some limitations. So the first limitation is that Dask computations are a graph, whereas Eliot is a tree. So if you think about the sum we did at the end, the fold, it took, the folding had a bunch of parents all going into one place and converging into one place. So it's not a tree because you had the task that has multiple parents. And so the way the instrumentation here works is there's in the logging messages, it actually tells you for each Dask task, it tells you what the parents are in the graph. So you have that information in the log messages, and it's not necessarily graphically shown in that tree all the time, but information is there when you read the log. So you as a human being can deduce that from the log messages. Another limitation is there's no built-in way to copy the logs into one place so you can view them easily. So in this example, it was all in one machine, so it was easy. If you're using multiple machines, you need to aggregate your logs somehow. There are lots of ways to do this. You can automatically upload to clouds like cloud storage, like a AWS S3 bucket. There's tools like Logstash for moving logs around. You can just use scopy to copy all your files to one place. And another limitation is that retries are not really supported by this mechanism. So if you end up retrying Dask tasks, because one of them failed, this will mess up the graph. This is solvable, but I haven't implemented this because I haven't heard any requests from users. But that is a limitation to be aware of. So that's Eliot in the context of Dask. It also supports the Persist API. So it has just like it has compute with trace, it has persist with trace. There's a bunch of APIs for creating log messages that I haven't gotten into for limited time. You can have pluggable serialization. So if you wanted to know how to log a small X-array object, you can teach it how to do that. You can use it outside of Dask, so it has like built-in support for things like async IO. You can even unit test your log messages. If you want to learn more about Eliot, it has extensive documentation, including how to use it with Dask. My website is pythonspeed.com. I have a whole bunch of articles about Python performance, using Python to process larger than memory data sets. Not all of it's Dask specific, but it probably interests people here. And also I write about Docker packaging for Python. And that's my contact info, and that is it.
Okay, thank you very much. We have a couple of questions in the chat, and we'll get through those before it's trivia time on another channel. So the first is, in the beginning examples, it was shown that all the inputs and outputs of actions were logged. How does this work for large inputs and output data types?
So the default is to just truncate them. So if you feed in a really large array, it will like take the first 100 values or something. I forget exactly. And sometimes that will be enough. That's just the default behavior. If you are, I have not implemented this, but it is definitely possible. If you are so one thing you can do is there are other APIs that don't just log all inputs and outputs to the function. So somewhere here, yeah, so here, this is a different logging API where you have to explicitly say which fields you want to log. And so if you use an explicit logging API, then you can just choose not to pass in the very large things. They won't end up
I guess that solves the next question too, which was, what do you do if there are things that can't be serialized, and you would have to use this mechanism?
Yeah, so you can, I didn't show them because I didn't go into too much detail, like the documentation covers it. There are alternative APIs where you can be much more explicit about what gets logged. And so you can log a summary, you can omit things. The thing where you log all inputs and outputs is just a convenience function wrapping the underlying APIs. You don't have to use it.
Okay,
it should be possible to serialize large things to temporary storage and then actually log everything, but that's a project.
Yeah. Okay, so we'll just a couple of simple questions. Is there a limit to log file size? I guess not in principle.
No, it's just a penny. It's like writing JSON messages to a file by default. You can
And
customize it.
can you use this for calls into C code, such as Python?
Python you can call back into Python. At the moment, there is not a low-level API. If someone was interested enough to, like, you can talk to me about it, and this ought to be doable, but it's not. From Python, you'd have to call back into Python. At the moment, this is a Python. I think someone actually implemented this in JavaScript, but at the moment, it could be possible, but right now it's not implemented in a low-level language.
Okay, thank you very much. We'll leave it there.